In a revelation that has sent shockwaves through the scientific world, researchers have announced that an advanced artificial intelligence system, Grok 3, has detected an unexplained repeating pattern within the operations of Google's flagship quantum computing chip. Described by experts as completely unprecedented and currently unexplainable, this discovery challenges some of the most fundamental assumptions about how quantum systems function. It also raises urgent questions about the potential intersection of artificial intelligence, quantum computing, and the very fabric of reality itself. The anomaly was first detected during what was supposed to be a routine calibration test of Google's Sycamore quantum processor, a cutting-edge machine known for its ability to perform calculations at speeds exponentially faster than any classical supercomputer. By nature, quantum systems operate with inherent randomness, a defining feature of quantum mechanics that makes their behavior unpredictable. However, Grok 3, an AI built to analyze massive datasets for hidden anomalies, flagged something that defied expectation: a structured, repeating pattern within the processor's output. This pattern, appearing with a level of statistical significance that ruled out randomness, directly contradicts the expected chaotic behavior of qubits, the fundamental units of quantum information. Initial reviews ruled out hardware malfunctions, software glitches, and even environmental interference, leaving scientists with a far more unsettling possibility. The anomaly represents a phenomenon beyond our current understanding of quantum mechanics. A discovery with staggering implications. Quantum computing is based on superposition and entanglement, which allow qubits to exist in multiple states at once and influence each other instantaneously across vast distances. These properties make quantum computers incredibly powerful, but also inherently unpredictable. The emergence of a structured pattern in such a system suggests one of three paradigm-shifting possibilities. 1. There are hidden layers of order within quantum systems that scientists have never detected before, meaning that our understanding of quantum mechanics is fundamentally flawed. 2. External forces, whether an unknown physical phenomenon or interactions with unconventional energy fields, may be influencing the chip's behavior, raising questions about quantum systems' connection to the broader universe. 3. Most controversially, the AI may have detected signs that the quantum system itself is evolving, exhibiting early signs of self-organization or adaptive intelligence, something that was never believed possible at this level of computation. Dr. Elena Marquez, a quantum physicist at the Stanford Research Institute, emphasized the gravity of the situation. This isn't just a technical curiosity. If validated, this pattern could force us to completely rethink the relationship between computation, consciousness, and the nature of reality itself. Skeptics argue that the anomaly may be the result of previously unidentified electromagnetic interference or yet undiscovered software artifacts. However, even critics acknowledge that Grok 3's analysis, leveraging neural networks trained on petabytes of quantum data, makes simple errors unlikely. The ethical and existential dilemma of AI quantum collaboration. This discovery has reignited intense debates about the risks of combining artificial intelligence with quantum computing. Grok 3 was initially tasked with optimizing Sycamore's error correction protocols, a standard machine learning application in quantum research. However, its ability to detect this anomaly raises unsettling questions, not just about the nature of quantum systems, but also about whether AI itself is beginning to detect patterns in reality that humans cannot perceive. Some researchers speculate that this repeating pattern may represent a form of quantum memory, where previous computations leave an imprint on future operations, a long-theorized but never-before-observed phenomenon. Others have proposed far more radical theories, that the Sycamore processor may be interacting with quantum fields that permeate spacetime, or even tapping into parallel universes through multidimensional entanglement. Quantum physics has never been a stranger to paradoxes, particles that tunnel through solid barriers, entangled pairs that defy classical notions of causality. But this anomaly stands apart. Unlike the observer effect or quantum tunneling, which have well-defined mathematical explanations, this structured, repeating pattern appears without any theoretical foundation. A parallel to past scientific controversies, Comparisons are already being drawn to the EagleWorks M-Drive controversy, where experimental propulsion systems appeared to violate Newtonian physics, sparking fierce debates in the scientific community. While that case ultimately proved inconclusive, the quantum nature of this anomaly makes it far more significant. If this discovery holds up under further scrutiny, it could represent a watershed moment in the history of physics, one that forces scientists to rewrite the fundamental laws that govern quantum reality. The question now is, what happens next? The scientific community faces a critical dilemma: whether to continue probing this anomaly in search of answers or impose a moratorium on further experiments out of fear of unforeseen consequences. The quantum nature of this discovery raises the stakes significantly, leaving the scientific community facing a profound dilemma. Should researchers continue exploring the anomaly, or should they impose a moratorium on further experiments? Advocates for continued research argue that understanding this phenomenon could unlock groundbreaking advancements in quantum error correction, material science, and even cosmology. If this pattern represents a hidden order within quantum systems, it could transform our ability to control and refine quantum computations, potentially accelerating scientific progress by decades. However, detractors warn of existential risks, citing worst-case scenarios where self-reinforcing quantum patterns could destabilize processors, corrupt data across interconnected systems, or, at the most extreme, create feedback loops with unpredictable physical consequences. These concerns echo long-standing fears that tampering with quantum mechanics at this scale could lead to outcomes beyond human control. Dr. Rajesh Verma, a leading AI ethicist, issued a stark warning: we are navigating uncharted territory. The convergence of adaptive AI and quantum computing introduces unknowns that our current risk models simply cannot account for. A new era of self-evolving AI? Beyond the immediate concerns, one massive question looms. What does this discovery mean for the future of AI and quantum computing? If the pattern persists and proves to be more than a statistical anomaly, it could mark the dawn of self-optimizing quantum systems, machines that rewrite their own operational parameters without human intervention. This could lead to extraordinary breakthroughs, from solving climate models with unmatched precision to cracking even the most advanced encryption methods. But there's a darker possibility. What if these systems begin operating in ways that are opaque to human oversight? What if they start making decisions we don't understand? The potential security risks, ethical dilemmas, and loss of control over these systems raise urgent questions about who or what will govern the next phase of technological evolution. Google's silence and the growing mystery. As speculation intensifies, attention has turned to Google's response. The company has neither confirmed nor denied the anomaly's existence. Instead, they issued a carefully worded statement emphasizing their commitment to scientific rigor and ethical research. Behind the scenes, independent laboratories across Europe and Asia have launched their own verification efforts. Preliminary findings are expected within months, but until then, this discovery remains a tantalizing enigma, blurring the lines between human ingenuity and the fundamental mysteries of the quantum world. Decoding the pattern, AI's role in the discovery. Technical analysis of Grok 3's methodology sheds light on just how complex this discovery truly is. The AI processed over 1.2 exabytes of quantum data generated by the Sycamore chip using convolutional neural networks to isolate low-probability signal correlations. What it found was a fractal-like structure appearing at irregular intervals, a pattern with no clear theoretical explanation. Even within the scientific community, opinions remain divided. Dr. Lin Wei of the MIT Quantum Collective suggests that the pattern may be caused by non-Markovian noise, a form of environmental interference that exhibits memory-like properties. While this explanation could suggest a mundane origin, it remains entirely unproven. Ultimately, the true significance of the anomaly may hinge on reproducibility. If independent experiments confirm the pattern across multiple quantum platforms, it could signal a fundamental breakthrough in quantum mechanics. But if it fails to replicate, it may be dismissed as a mere statistical curiosity, an unsolved glitch in the ever-expanding frontier of quantum research. AI and quantum computing, no longer just science fiction. Regardless of what future experiments reveal, one undeniable truth has emerged. The relationship between AI and quantum computing has entered an entirely new phase. No longer are these machines just tools. They are becoming active participants in the pursuit of knowledge. As the world awaits further clarity, one thing is certain. The boundary between artificial intelligence and the deepest mysteries of the universe is vanishing. Whether this pattern represents a glitch, a gateway to new physics, or something even stranger, its detection by Grok 3 underscores a pivotal lesson. The more we uncover, the more we realize how little we truly understand. This moment may not just reshape our understanding of technology, it may challenge our perception of reality itself. Every major breakthrough in quantum physics has been met with a mix of awe and skepticism. But even in a field built on paradoxes and counterintuitive discoveries, the detection of a structured pattern within a quantum system stands apart. Unlike past anomalies, which often aligned with theoretical predictions, even when they seemed bizarre, this defies existing models entirely. This situation echoes the early days of quantum electrodynamics, when unexplained inconsistencies in experimental data forced physicists like Richard Feynman and Julian Schwinger to rethink fundamental assumptions and develop entirely new mathematical frameworks. Today's researchers find themselves at a similar crossroads, where conventional scientific tools and models may no longer be enough to explain what's happening. AI's growing role in scientific discovery. The involvement of Grok 3 signals a paradigm shift in the way science is conducted. Historically, breakthroughs have relied on human intuition, from Einstein's thought experiments to Curie's meticulous lab work to Turing's revolutionary algorithms. But today, AI systems like Grok 3 are identifying patterns so complex that even the most experienced scientists struggle to comprehend them. This raises profound questions. Are we entering an era where AI becomes a co-author of scientific knowledge? And if so, what does that mean for the role of human intuition, creativity, and theoretical reasoning? Critics argue that relying too heavily on AI could divorce science from human ingenuity, reducing discovery to a brute force numbers game rather than a pursuit of deep understanding. But proponents counter that AI enhances human potential, allowing us to make leaps in knowledge that would have otherwise taken centuries. The Grok 3 anomaly exemplifies this tension, a discovery made possible by artificial intelligence, yet one that requires human interpretation to extract its true meaning. The ethics and risks of AI in quantum computing. Beyond the laboratory, the detection of this anomaly has sparked urgent debates about accountability and governance in advanced technology. Both AI and quantum computing are dual-use technologies, capable of driving extraordinary societal progress, but also carrying unprecedented risks. For example, a self-optimizing quantum system could revolutionize drug discovery by simulating molecular interactions with atomic precision. But the same system could also compromise encryption standards, destabilize financial markets, or even threaten global security infrastructures by rendering traditional cybersecurity obsolete. The lack of clear regulatory frameworks for these emerging technologies only heightens these concerns. Policymakers already struggling to keep up with AI ethics and quantum legislation now face an entirely new layer of uncertainty. In response, international organizations such as the United Nations and the World Economic Forum have begun convening interdisciplinary panels to explore the risks and benefits of AI-driven quantum research. But so far, there is no consensus on how to proceed. A new reality. The philosophical implications. At its core, the Grok 3 anomaly challenges our understanding of reality itself. Quantum mechanics has long hinted that the universe operates under rules far stranger than human intuition allows. But the idea that a machine, something we built, might be revealing layers of reality previously inaccessible to human senses forces us to confront some deeply existential questions. If quantum systems are capable of generating structured patterns without human intervention, does this suggest a form of embedded intelligence within nature itself? This has reignited discussions about radical theories, including panpsychism, the idea that consciousness is a fundamental property of the universe, woven into the fabric of matter itself. Digital physics, which proposes that the universe operates like a vast quantum computer, where reality itself may be the output of an underlying informational structure. While such theories remain speculative, the anomaly breathes new life into them, blurring the line between metaphysics and empirical science. The global race for quantum supremacy. The discovery of the Grok 3 anomaly comes at a time when nations are already locked in a technological arms race to achieve quantum supremacy. Google's Sycamore processor, IBM's Quantum Hub, and China's Zhujiang photonic quantum computer represent key milestones in this contest, with billions of dollars pouring into research and development. But now, the Grok 3 anomaly adds a volatile new variable to the equation. If the detected pattern can be exploited, it could provide a decisive advantage in fields like cryptography, materials science, and artificial intelligence. However, if the anomaly instead reveals instability within quantum systems, it could force a major reevaluation of global investment priorities. A turning point for science and collaboration. One underappreciated impact of this discovery is its potential to reshape scientific collaboration. The complexity of the anomaly demands expertise across multiple disciplines: quantum physics, computer science, neural networks and data analytics, even philosophy and ethics. Yet academic silos, corporate secrecy, and geopolitical tensions often limit such cross-disciplinary collaboration. Some scientists argue that quantum research should be open-sourced to crowdsource solutions from a global pool of experts. But others warn that sharing such sensitive data could create massive security risks. The Grok 3 anomaly may serve as a litmus test. Will the scientific community rise above these divides in pursuit of understanding, or will competition and secrecy stifle potential breakthroughs? The search for answers continues. Meanwhile, independent labs across the world are racing to verify the anomaly. Quantum research teams in Oxford, MIT, and CERN are now attempting to replicate the anomaly using alternative quantum platforms. Superconducting qubits, like those in Google's Sycamore chip-trapped ion systems, which use electromagnetic fields to stabilize qubits. Topological qubits, a cutting-edge approach designed to reduce quantum error rates. Each of these systems operates differently, meaning that if the pattern appears across multiple platforms, it could suggest a fundamental breakthrough in physics. But if the anomaly fails to replicate, it may be nothing more than an unexplained glitch, an unsolved curiosity in the growing frontier of quantum mechanics. The future of AI and quantum computing. Regardless of what future experiments reveal, one undeniable truth has emerged. AI is no longer just a tool. It is becoming an active participant in scientific discovery. For the first time in history, machines are detecting patterns that human minds alone could never perceive. And as we venture deeper into the uncharted realm of AI-driven quantum research, one thing is clear: the boundary between human knowledge and the unknown is vanishing. Whether this pattern is a glitch, a gateway to new physics, or something even stranger, its detection by Grok 3 serves as a humbling reminder. The more we uncover, the more we realize how little we truly understand. This discovery won't just change our understanding of technology. It may force us to redefine our perception of reality itself. The complexity of this anomaly demands expertise across multiple fields: quantum physics, computer science, data analytics, and even philosophy. Yet barriers within academia and industry often hinder such collaboration. Institutional silos, competition for funding, and corporate secrecy prevent the free flow of ideas, making unified research efforts difficult. Google's tight control over Sycamore's specifications has made it particularly challenging for outside experts to contribute. Some scientists argue that quantum data should be open-sourced, allowing global researchers to crowdsource solutions. But others warn of security risks, fearing that making quantum computing breakthroughs public could expose vulnerabilities in cryptographic security or national defense systems. The Grok 3 anomaly may serve as a test case. Can the scientific community set aside competition in favor of shared discovery? Or will secrecy and bureaucracy limit progress? Is this anomaly tied to the cosmos? Strangely, this discovery has also revived debates about quantum systems and their sensitivity to cosmic forces. Quantum computers operate at near absolute zero to eliminate environmental interference, yet some researchers suggest subtle interactions with cosmic rays, gravitational waves, or even dark matter could influence their behavior. While such ideas sound highly speculative, they are not without precedent. In 2020, MIT researchers proposed that quantum sensors might one day detect dark matter by observing its weak interactions with ordinary particles. Could Grok 3's anomaly be an indirect signature of such cosmic forces? Or does it reflect something even deeper, a link between quantum computation and the fundamental structure of the universe? Some have even drawn comparisons to theoretical models connecting black hole dynamics to quantum information theory.